In this video, I will discuss using the t-distribution to find confidence intervals. This is discussed in the text in section 7.4. Okay, in the previous lecture on confidence intervals, in which we used the normal distribution and the z-values, there were some assumptions. It was assumed that either or both the population standard deviation was known, or that the size of the sample, sample size was so large that you could use the distribution of the sample size in place of the population standard deviation. The standard deviation sample size in place of the population standard deviation. So you had to have a large sample size, or you had to know the population standard deviation. So in some cases this might not be true. You might not have that information, but you can still construct confidence intervals by using what's called the student's t-distribution. For homework, you can look up why it's called students. So in the previous case, when we were using the normal distribution, we called those multipliers z alpha over 2. Now, appropriately, we're going to call them t alpha over 2. Now this t-distribution looks bell-shaped, but it is not normal. It's sort of heavier in the tails. But it changes and approximates, becomes closer and closer to the bell-shaped curve as n increases. And the parameter that's used to describe that, the size of the sample, is called degrees of freedom. And the degrees of freedom is the sample size minus 1. Here's some sample t-distributions. I think you've already made some in this class. But the black line here is for the degrees of freedom approaching infinity, and that means very, very large samples, and it is close to bell-shaped. And it's, well, at that point the limit is bell-shaped. But you see, if you have smaller numbers for the degrees of freedom, then it's elevated here in the tails from being a real bell-shaped curve. So your t-distribution is still symmetric, but and approximately bell-shaped, but it's just heavier in the tails, and it requires the parameter df, degrees of freedom. Now the confidence intervals look just the same. Here's the confidence interval using a normal distribution with the z, you see the z alpha values in it. Here's the confidence interval using the t-distribution. The difference only is that for the normal case, this multiplier is z alpha over 2, and for this case it's t alpha over 2. And it's, instead of pretending we even know the population standard deviation, we write S here, meaning the sample standard deviation. And you can find those t alpha over 2 values by looking in the in a table, or you can find them in R. Here's just a sample calculation, and it was done using the tables. So let's say the mean is 15. No, I'm sorry, sample size is 15. The mean is 36.2, and the standard deviation is 5. So what we have in this case, mu for the sample, which Mendenhall calls y bar, is 36.2. N equals 15, and the standard deviation is 5. Because n equals 15, the degrees of freedom are 14. It's always 1 minus the degrees of freedom. Okay, the general equation looks like this: y bar minus t alpha over 2 times s, we know what s is, it's 5, divided by the square root of the sample size n, which is 15. So to get both sides, it's plus or minus that value. All right. So you can see what we have here. Here's the mean, 36.2 from up here. The sample size is 15, so that's your square root of n in the denominator. Standard deviation is 5 for the sample, so you see the 5 up here. Now the 2.145, that's the value for T alpha over 2 that was obtained from the tables in this case. So having calculated to this, and it was for 95% confidence level. Okay, so if it's 95% confidence, then alpha is 0.05. Alpha over 2 is 0.025. Okay, so we're saying here with 95% confidence, the population mean lies between 33.43 and 38.97. These calculations can be done in R, and there's some on 2 for the homework. But if you look in the R tutorial, I did exactly these calculations. Look under confidence intervals for t distribution.